Everyone, hi, could we have your attention? All right, I have a few announcements about the upcoming midterm, which is 1 week from today. First of all, the format of the midterm will be exactly the same as last time. It'll be 6 short answer questions. You choose 5. The rooms, we have to make a few changes to the rooms because we couldn't get the same ones as last time. So I will send out an email to everybody. I will send out a reminder email the night before. I will post it on the website. Please don't go to the wrong room because we can't accommodate a lot of people in the wrong room. The other thing is we will be having a review session on Friday at 10 a.m., 10 to 11 in Science Center C. Like last time, this will be all Q&A, so please come with your questions. It will be videotaped, but the problem is that we don't control the videotaping. Another office does, so I don't know if it will be posted in time for you to use it for the midterm. So if you want to make sure you get the review session, please show up in person. Thank you.
And those of you that missed these little remarks about the, well, those of you that heard the remarks about the midterm, tell them to your friends who aren't here and who might want to know them. This is the part of the semester where it becomes increasingly difficult for me to compete with the nice weather. It is really nice, yeah. Any questions about the material so far? Okay. Last time we discussed the ways that online and offline networks resemble each other and the ways that they do not. We talked a little bit about how influence might work online. We reviewed the genetic antecedents to, and to a lesser extent, the genetic consequences of social networks. And we talked a little bit about how an understanding of social networks can help to bridge the gap between methodological individualism and methodological holism. And today, what I'm going to be talking to you a little bit about is what one might actually do with knowledge of networks to make the world better. So I spent like the first 5 or 10 years of my life studying networks, sort of trying to understand how networks form and operate. What's the sort of structure and function of human social networks? But over the last 5 years, my colleague James Fowler and I, we've become very interested in answering what we call the so what question. So what? So what if we can understand human social networks? What, if anything, can we do with that knowledge to make the world better? And so today I'm going to give you some examples of the kind of ways you can exploit a network understanding of human interactions in order to intervene in the world to improve outcomes for individuals and for collectivities. Now, there are 2 broad ways one can think about potentially exploiting these social processes. And in fact, there are 2 ways that you can imagine altering a social network. You can manipulate the connection. You could change the structure of the interactions between the constituent individuals, or you can manipulate contagion. Given a fixed structure, how can you manipulate what flows through the network, how it flows, where it flows, and so forth? Now, to manipulate connection, you have to actually rewire social networks, cutting or forming ties, for example, and this is potentially quite tricky. For example, how do we affect who is friends with whom? If I wanted to force you 2 people to be friends with each other, it'd be very difficult to enforce that kind of a domain. Or if I wanted to split you 2 and say you can't be friends with each other, it would be difficult to do that, except in certain very specialized circumstances. There are some examples, of course, of this. For example, military squads. The military takes people who are strangers to each other and fosters group cohesion, as we saw the little brief cartoonish example a couple of lectures ago. Weight Watchers, where strangers can come together. Something's at stake. They wish to lose weight. They come together and they can support and affect each other. Alcoholics Anonymous, and other sorts of health-related interventions. To manipulate contagion, however, we have to alter what's flowing through the network. For example, by choosing who to target with new information or behavioral interventions, like some of Tom Valenti's work on seatbelt use, smoking cessation, substance use, and so forth. And many people have been trying to do this, and we still don't have a complete understanding of why some things go viral and some things do not. And this type of manipulation of connection and contagion can take place both in the online world and in the offline world. And this whole area is under very active investigation at the moment. And while it's clear that social networks can be matter and that they can be manipulated and exploited, many aspects of this are still being worked out. And finally, at the end of the lecture today, I'm also going to introduce another idea to answer the so what question, which is not just how we might manipulate networks or intervene in networks, but also how we might extract information from networks in a kind of twist that I think is sort of illustrative. So here's one example. Let me sort of illustrate one example using one particular set of experiments that was done to sort of really sort all this out. This was a paper published by Damon Santola not too long ago. Damon became very interested in how things might spread within networks, and he conceived of a set of experiments in which the topology of the network could be experimentally controlled or manipulated, and then we can evaluate the spreading dynamics within the network of different sorts of phenomena. Now, these two network pictures both contain 128 individuals, on the right and on the left. And what's also interesting about these two networks is that both on the right and on the left, every single vertex in the network, every single node, has exactly 6 connections. So everyone in the left, everyone on the right, this yellow dot is connected to the 6 red dots, and every other dot is connected to 6 dots. And similarly here, every dot is connected to 6 and only 6 dots. Now, if you were a human being and you were in one of these worlds, you would be unable to tell me which world you occupied. To you, this would seem exactly the same. And for everyone in that same system, it would seem the same. You would say, I've got 6 friends. How many friends do you have? You've got 6 friends. How about you? You've got 6 friends. And you would get the same answer, and that would be the same perception, regardless of which of these two worlds you happen to occupy. Okay, now let me cultivate an intuition in you. Let's say a germ is spreading within this network, and you can infect one person, say the yellow dot. In which of these two networks, the random network, where the ties are randomly wired, or the neighborhood network, or the ordered sort of regular lattice network on the right, in which of these two networks do you think that the epidemic would spread faster and more completely, on the left or on the right? Raise your hands if you think the germ would spread faster and more completely on the left. Raise your hands if you think that the germ would spread faster and more completely on the right. Raise your hands if you have no freaking idea what's going on. Yeah. Well, it turns out that the correct answer is on the left. The germ will spread much more rapidly if a person's infected and is a part of a kind of a random network. This individual is infected. In the next time step, these 6 red dots are infected. In the next time step, 6 other red dots for each of those 6, and whoosh, it spreads dramatically through the system. Okay? Incidentally, the same kind of thing happens if what's spreading is not a germ, but a piece of information. Let's say you wish to communicate to people whether it rained yesterday, or what the Dow Jones Industrial Average closed at yesterday. Things like that, epidemics of information or of germs, spread more effectively in random networks than in ordered or regular lattices. And this was the state of affairs. This is what people thought was generically true for all contagions, until Damon and some colleagues began to think about ways to explore how the topology of the network, which is potentially manipulable in online interactions, could affect the speed and completeness with which things can spread within the system. And so they conceived of this experiment in which people were brought into virtual laboratories and they were dropped into different worlds which had this experimentally controlled topology on the left and on the right. Now, what they tried to study, however, was not something that could spread like a germ or an information, but rather something that spread by a process we're going to call complex contagion. Something called simple contagion, germs and information spread by a simple contagion. But certain other things, for example, like smoking cessation, spread by complex contagion. Why is that? Well, if I am about to get sick, and you 3 people are my friends, if I have contact with you and you infect me with a germ, subsequent contact with her who has the same germ doesn't increase the probability that I'll become infected. Or if I want to say, what did the Dow Jones Industrial Average close at yesterday? I say, what did it close at? You say this, thank you very much. Maybe you say the same piece of information. It doesn't help me at all that you've said the same thing. It may help for those of you paying careful attention in confirming or reducing uncertainty, but leave that aside for the moment. Assume that there's high fidelity transmission. Now instead consider the possibility that I'm thinking about whether to quit smoking and these 3 people are my friends. Do you think that whether she quits and she quits and she quits, do you think that with an increasing fraction of my friends who are quitters, I'm more likely to quit? In that kind of a situation where the thing that's spreading is a kind of behavior or something we're going to call complex contagion, it turns out paradoxically that this network is much more efficient at transmitting complex contagions. And the intuitive reason is that if this individual starts the epidemic, this yellow dot, and the 6 dots are infected, these additional dots here that are right on the frontier are connected to multiple people who have already experienced the contagion, which flips them. And as a result of flipping, you get this wave movement. Whereas on the left-hand side, each of these isolated individuals is connected to no one else but the original source who's also adopted the contagion. Do you see what I'm saying? So it turns out that things that spread by complex contagion, like behaviors, are more likely to spread in the right-hand side in regular lattices or neighborhood-structured networks than in the left-hand side like random networks. Now this is very interesting because remember, from the point of view of the individuals, they have no idea what world they're in. And what that means is that if we understand how things can spread and can control human interactions, we can pick a set of interactions that fosters the emergence of the desirable property. We can experimentally manipulate in online worlds and to some extent in offline worlds how people interact by wiring the network correctly, specifying the wiring diagram, and in so doing can facilitate the spread of whatever it is that we might want. So this raises the possibility that the amount of social reinforcement we give to people, for example, in this application it was a health habit, the experiment was a behavior involving health, may be more important than who is encouraging them to do so. In other words, a local community network of friends and neighbors may be more important than, for example, some arbitrary, like, external individual. In other words, whether you adopt a behavior may have to do with the structure of the network around you more than who is saying what near you, for example. Now, we've also conducted some experiments in our lab to assess the power of network rewiring to stabilize cooperation. And in this experiment, we took 785 subjects that we recruited from around the internet. These were Amazon Mechanical Turk workers, anonymous individuals. We paid them small amounts of money. And we brought them into this virtual laboratory, and we wrote some software to do this. We brought them into this virtual lab, and we asked them to play a kind of public goods game that we've talked about in prior lectures, where they could interact with each other. And in one of those virtual worlds, we dropped individuals into a fixed lattice. Not to a fixed lattice, into a fixed network, a network that couldn't change across time. So here's a network of individuals, and at the beginning, we colored the defectors red and the cooperators blue. So this is how they play. Do they cooperate with their neighbors or do they defect? And what you can see in this image is a widely observed phenomenon in the social sciences. There have been hundreds of papers on this topic. What you find is that as time goes by, the world gets taken over by defectors. What happens is at the beginning, these guys, the blue guys, are cooperators, but there's some people around them that take advantage of them, and they say, to hell with that, and they switch to defection. They stop cooperating with their neighbors because they don't want to be exploited by their neighbors. And so gradually, everyone becomes a defector. All the dots become red. You got a little cluster on the corner here of cooperators who are more connected to each other, which is sort of a hint about what I'm going to be getting to in a moment. Okay? Now, what if instead of forcing people to be stuck with their neighbors and say, you must play this cooperation game with your neighbors, and everyone else in the system is playing with their neighbors. What if instead we also allow people to rewire their connections? And after each round, they get to decide, do I want to stay connected to this person or not? So instead of only permitting them a kind of behavioral reciprocity, I'm going to play the prisoner's dilemma with you, you can cooperate or you can defect. If you defect, I say to hell with you and I defect. If you cooperate, I say, oh, she's nice, and I cooperate. And so instead of just having that behavioral tool at my disposal, where I can either cooperate or defect, and I reciprocate what she does, in addition, I also have the tool of saying, hey, you know, you're a defector. I'm cutting the tie to you. To hell with you. I'm going to go work with her instead. Okay? So you allow a kind of rewiring. In that type of situation, what happens amazingly is that you can actually sustain cooperation by manipulating the rules of engagement, the rules of wiring, and instead of cooperation disappearing as it does here, it gets maintained. All the dots remain, or the same number of dots remain blue going across. In fact, this network gets rewired, and ultimately this network assumes certain mathematical properties that are actually very interesting, and the empirical distribution of those properties resembles the kind of way in which we order our social lives. So to summarize the results from that experiment, which we published just a year ago now, here on the y-axis is the fraction of players in these replicates of the experiments that are cooperative, and here's the round of gameplay. They played for about an hour and a half, these subjects, playing with their network neighbors, anonymous neighbors that they'd been assigned to. And here is the fixed network in green. Cooperation always starts at around 60%, and then in green it kind of over time declines. I just showed you that. Here is a situation in which we have random rewiring, so at every round you just get randomly assigned new neighbors. Cooperation also disappears. And here in blue is what happens when you permit the network fluidly, dynamically, people to rewire their network. You can maintain or preserve cooperation. Here in yellow is a fourth treatment in which we had a viscous dynamic situation. We permitted rewiring, but only a little bit, not enough. The point is that you can construct, here it is an example where we can foster the emergence of cooperation in a social system by manipulating the rules of interaction, by manipulating the rewiring, the permissible rewiring within the network. And in fact, we use cooperation as a model system in my lab, but it doesn't need to just be cooperation. We use cooperation because there's some nice measurement properties, but there are all kinds of other properties of groups like innovativeness or health or other kinds of things that you can imagine depend on how people are connected to each other, how they are wired to each other. Now, a totally different class of intervention that you might do has not to do with connection or the wiring of the network, for which I've now shown you 2 experimental examples, but rather with the manipulation of contagion. So imagine now that we're going to want that this is a real application. We're doing this in the lab in places around the world, as I'll show you in a moment. Imagine now that your job is to go to a developing world village or to a high school classroom or to a factory, and you want to move a mountain. You want to change the group's behavior. For example, let's say you want to get people in Uganda to use anti-malarial bed nets. Or villages in Honduras, you want to get them to clean their water better, okay? So one possibility is that you go to these villages and you map the networks of the village. So in the past, you might not have known these ties at all. Here are the residents of this village. Here now we've mapped the ties of them. Here's the same village counterfactually on the right. And now let's say you only have enough resources to reach 6 people. And let's say you pick the 6 people at random, okay? So, or you might, if in the old-fashioned days, you might pick them based on who's the eldest or who's has the highest education or the biggest land holdings or whatever. But for the sake of this illustration, let's say you pick them at random. And so you're going to experimentally randomly assign half the villages, nobody will get the intervention, which is an educational intervention about clean water, and half the villages, 6 people at random from each village, will get the intervention. You with me? Then you come back a year later, and what you measure is, this is the key part, you measure not the response to treatment among the individuals who were treated, you measure the response to treatment among the individuals who were not treated, and compare that to the untreated village. So you come back a year later and you say, okay, how many of these 6 people adopted the clean water intervention? That's old-fashioned. No, what you measure is how many of the untreated people in this village adopted the intervention, and you compare that to the control village where no one got the intervention. And the contrast between those two tells you what the spillover effect is. It's a measurement of peer effects under control, under the controlled treatment situation. It's a measure of the pure contagion of the intervention. So what you are doing here is you're trying to understand, do things spread? Does the thing spread at all? And in order to do that, you randomly target some people in this system, and in this system you leave everyone untargeted, and then you compare the adoption amongst the untargeted in both systems afterwards to see, is there interpersonal spreading in the system? People with me so far? Now here comes the cool part. What if instead of picking these 6 people at random, now that you've mapped the network, you strategically target individuals who are in the center of the network, individuals who occupy particular topological locations. So you say, aha, I can only reach 6 people in this village. I want to change the world. I want to go to Uganda or Honduras or Uttar Pradesh and persuade the women there to adopt better practices for neonatal childcare. And I can only reach some of the people. Wouldn't you love to reach the people who are located in the network in such a fashion that if you persuade them to change their behavior, you get bigger spillover effects and more spread within the system? You would. Well, you can use network science to identify who are the individuals within that system that you should optimally persuade to change their behavior, because if you do, they'll move the whole village. So now in this situation, you can do an experiment in which you randomly assign certain villages to have people picked, let's say, according to the centrality heuristic, and then you look at the response of the untreated people in this village compared to the untreated people in this village, and then you can see whether the peer effects under acceleration, if you can accelerate the peer effects and get even bigger bang for your buck by still reaching the same number of people. Or you could take advantage of other properties like the transitivity idea that we introduced a few lectures ago, and now you can begin to ask even more subtle questions. So now the contrast is this village, 6 people were randomly chosen. In this village, you pick these 6 people in the same cluster. And in this type of experiment, instead of comparing the response of the untreated people, here you compare the untreated people in the treated village to the untreated people in the untreated village in this experiment. In this experiment, you compare the treated people in the treated village to the treated people in this other treated village. And here the question is, okay, let's cultivate intuition. You're going to target this 6 people at random with a clean water intervention. And here you're going to target 6 people that are clustered. In which, I'm going to ask you now, in which of these 2 villages do you think a higher fraction of the treated people will respond? In which of these 2 villages, for example, do you think that 5 of the 6 will adopt your intervention? And which of these 2 villages do you think that 1 of the 6 might adopt your intervention? Okay, who thinks that the left-hand picture, more of the yellow dots will adopt the intervention? Raise your hands. Who thinks on the right-hand picture, more of the yellow dots will adopt the intervention? Excellent! Because there's complex contagion. These people are clustered. They're going to reinforce each other's behavior. So, another idea now is that if you have finite resources and you're trying to change the world in particular villages, or you're trying to get school kids to stop bullying each other, or you're trying to get kids to wear their seatbelts, or factory workers to be more innovative or productive or practice safe practices, an understanding of the network of interactions gives you the opportunity to identify clusters of individuals if you have a budget constraint. If you can reach everybody, God bless you. But if you can't reach everybody and you have a budget constraint, you can shrewdly target individuals and target them in this fashion, not only getting more of the untreated people to respond, but also more of the treated. So it's, from my perspective, a whole new world of understanding how we might intervene in systems. I care about public health interventions, but of course, these types of ideas can be more broadly applied. And so in the lab, we've begun to do experiments of just this kind. Last summer, we sent some graduate students and some undergraduates, former SOC 190ers, went to this village went to this set of villages in the highlands of Honduras. This is a typical situation in a typical village in this area. And we mapped, in conjunction with some people at the University of Michigan, with Derek Stafford and Alex Hughes, we mapped the networks of these villages. So here now we overlay the location of the dwellings of the individuals in these little hills and valleys, and we have all the network ties, which are faintly shown there, between the people in each of these villages. And then we randomly assign the villages, just like the experiment I just showed you, to see could we foster the adoption of clean water interventions in these villages by not only delivering the intervention, but delivering it in a network-informed way. So, for example, we could target, in this experiment, we had a number of interventions. We had a vitamin intervention, a kind of a toothbrushing intervention, a clean water intervention, that's a little Clorox bottle, a seed intervention, and I forgot what that intervention was. Eventually, we went with these 2 interventions, and we started, and I won't go into this, we started looking at the spread of the intervention within the networks. And here's an example of one of my graduate students, Allison Huang, and I don't know if any of the undergrads are in this picture, I can't see, sort of explaining to people how they go about using the clean water intervention, the people who were carefully chosen according to their network position. Then we came back a few months later to see everything that I just described to you, and we're analyzing the data right now. So that's a second kind of way that we can intervene in networks. We can intervene not only by manipulating the wiring of the networks, as I've just been explaining to you, but also by other sorts of procedures, such as targeting interventions, where we pick people shrewdly according to their location within the network, with a fantasy, we hope soon to be the reality, that in so doing, you can foster rapid transmission within the system. Are there any questions so far? Yeah. Something like that, yes, exactly. They spread in both, so germs will spread in both, and complex contagions will spread in both. But the intellectual idea there is that certain kinds of things, which we may or may not be able to know about ex ante, but which in general have to do with behaviors that require reinforcement, certain kinds of things require reinforcement by individuals, and so a clustered kind of organization of the network will be optimal for those kinds of things. Incidentally, a germ will spread much more slowly in the ring lattice. So, for example, conversely to the complex contagion, if you infected one individual here, actually for the infection to get to this individual takes forever. Bang, 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 much longer. Okay, so it's not like, as usual with these networks, it's not like one thing is best for everything. It depends. Did I answer your question? Yes. Other questions? Yeah, in the corner there.
What happens when we look at groups in the center? So we said clusters are better for adoption within the group, but we see better spillover if we have the central people very transitive, or if we have 2 different groups of central.
Okay, so I could spend a whole semester talking about that topic. And today's is just to illustrate, I picked the central individuals. Actually, it's much more complicated than that. You don't just pick, one of the reasons, for instance, just to cultivate the intuition, let's say you map the eigenvector centrality of all these, you computed the centrality of every person in this image, and then you ordered them from most to least central. It actually would be foolish to target the 6 most central people, because they're all going to be connected to each other. So you want like not the 6 sequential pearls on a string, you want like every other or every third pearl on the string, for instance. And there are algorithms you can use to do that, like k-coordinates and other kinds of things I won't go into today. Yeah, next question. Yeah, somewhere here? Other questions? Isn't this totally cool? It's like, I love this. Okay. All right. So now here's another idea. Some more recent work of ours has also shown how information might be extracted from networks rather than introduced into networks, okay? Totally different idea. So now instead of targeting individuals within the system to deliver the information to them, now the idea is how can we extract the information from the system, providing, as it turns out, a whole new way to predict epidemics, as I'll show you, well before they strike the general population. Now, as most of you probably know, for any kind of infection or diffusion of innovation, there's a so-called S-shaped diffusion of innovation curve or adoption curve. Here's the percentage of individuals affected by a contagion or by a product adoption, you know, for fax machines or some new, what is it, Snapchat or whatever's popular now. How popular is it's probably maybe already fading as far as I know, Snapchat. Completely missed that, which is actually probably for the best. So here's time here, and here's the percentage affected. So at the beginning, nobody is infected with a germ or has adopted the product. At the beginning, you get the few early adopters, and you get the epidemic growth curve. It explodes, and eventually it saturates the susceptible members of the population, for instance, maximizing at 100%. So you get increasingly hard to find unaffected individuals or hard to persuade individuals who haven't yet adopted to adopt. So you get this S-shaped, this classic S-shaped diffusion of innovation curve. And part of this has to do that as more and more people adopt the product or the germ, it affects the propensity of others to adopt, and this property plus the finite size of the population gives rise to this classic S-shaped epidemic curve. Now, remember how last time we talked about the variation in network position, and I cultivated the intuition in you that if a deadly germ is spreading through the network, remember you all, or most of you had this intuition, it was better to be D than C. Because you had the intuition that if you were C, you would be more likely to get whatever's spreading through the system, if you have higher network centrality. Well now, and also another thing that I can cultivate is, who do you think is at greater risk if a germ is spreading, B or D? Germ is spreading, a germ is introduced randomly into the system. Who do you think is going to be more likely to get it ultimately, B or D? Raise your hands if you think B is more likely. Raise your hands if you think D is more likely. One of you, why do you think D is more likely? Yeah, so D is connected to 6 people, and B is connected to 4 people. So people with more friends are going to be more likely to get a germ, right? If you have a higher degree, like in the limiting case, if you had no friends and if you were a hermit in Mount Athos in Greece and you never talked to anybody, you're not going to get any epidemic contagions, okay? So the degree matters. So it's not just in centrality. And now do you have an intuition about A and B? It turns out that B is going to be more likely to get whatever's spreading than A. Higher transitivity will be associated with a decrease in the probability of getting the infection because you're insular. You're only hanging out with your own little fraternity or sorority. Okay, you don't talk to anyone else unless and until you get someone introducing the germ into your little group, it doesn't take off. All right? So we cultivated this intuition. Now what it means is that if we could identify central people and monitor them passively or actively, this gives us a tool to identify epidemics before they strike the general population. So if you can map networks, figure out who's central, and just spy on them, and watch and see what happens, then if you see them being infected by a germ, it means the epidemic's about to strike soon the general population. Now the problem is it's not always possible to actually map networks. It can be actually quite difficult. So if we could only monitor 6 people in this system, we would pick these 6 people, actually a little bit more spread out, but for now just assume these 6 people within the system. And that these 6 people would give us more information about the likelihood of spread of the germ or piece of information than 6 people chosen at random from throughout the system. So the intuition here is that as shown in the dotted red line, this is the epidemic growth curve in the population, in the dotted red line, and the curve would be shifted to the left in the population of individuals who are central. Or put another way, if instead of the cumulative incidence you looked at the daily incidence, the epidemic should peak some amount of time delta t earlier in the central people than in the random people within the system. Does everyone understand this idea? So the epidemic should spike and peak sooner in people in the center of the network than from a random draw of people within the network. Which means if we can identify the central people, we can forecast the future of epidemics, not just of germs, as I'll show you in a moment, but of anything that spreads within the system. Now the problem is we can't always map networks. So it's not always feasible. It can be expensive or impractical or in fact impossible. So how could we figure out who the central individuals are without having to map networks for a whole population, whether 100 students or people or 10 million people? Well, it turns out that there's a mathematical fact about social networks that is summarized. It's known as the friendship paradox, and it's summarized by the claim that your friends have more friends than you do. Did you know that? Your friends have more friends than you do. Actually, your sexual partners have more partners than you do too, but that's another topic. And the reason is that, imagine that we have a party hostess who has a party, and she invites 100 people to come, and all those people know nobody. So we have a very simple network, one person in the middle connected to 100 people. Every one of those 100 people has one friend, that's the party hostess, but the party hostess has 100 friends. So if you draw people at random from that graph, and you ask them to nominate a friend of theirs, they're all going to nominate the party hostess. So for 100 of the 101 people, their friend will have more friends than they do. In fact, many more. Everyone with me still? And in fact, only one person for the party hostess will her friend, she says, oh, I can pick one of these 100 people. Only in this pair will she have fewer friends than I do. So this is known as the friendship paradox. And actually, it's a very basic feature of social networks, and it arises from the variation in the degree in networks. The average person has mu friends, but the friend of an average person has mu plus the variance divided by mu friends. And I won't go into that except for the few of you that understood what I just said. So what this means is that friends of randomly chosen individuals, if I could go to a network and pick people at random and have them nominate their friend, it's a mathematical necessity that in expectation on average, those friends will have more friends than they do. The friends of random people will be more central and have higher degree than the randoms. And I can cultivate that intuition in you by, for instance, looking at the edge cases. For every one of the people on the very periphery of the network, if I pick one of them and ask them to nominate their friend, by construction they can only go inward, and the person they nominate will have many more friends than they do. Do you see that intuition? The thing that puts them at the edge means that when they nominate a friend, I nominate this guy, he's got to have at least 2 friends, otherwise he would be on the edge as well. And this person has 7 friends when they nominate. And it turns out it works that way all the way through the system, not just in the edge cases. If you pick the 6 yellow dots at random and you have them nominate their friends will be more central in the network by necessity on average. Everyone with me still? Well, what this means is that you can exploit the friendship paradox to identify a group of central individuals without mapping the network. You don't even have to map the network to find central people. I can pick you guys, I can say, okay, each of you nominate a friend of yours. And I go to that group of friends, and those friends, compared to this group, will be more central than you guys are, it turns out. And we tested this idea with an outbreak of H1N1 flu with Harvard students in the fall of 2009. Raise your hands if you were part of that study. Yeah, there are fewer and fewer people still left. Great. By next year, they'll be gone. So what we did is we gave students, did you guys claim the JP Licks ice cream coupons? Yeah, so we bought like thousands of dollars of JP Licks ice cream things for $5 or $10 or $20, I don't remember, and we asked the students to sign up, and we said to them, look, we're gonna email you twice a week. We asked individuals, we picked them at random from the Harvard undergraduate population, we had them nominate their friends, and we formed 2 groups, the random group and the friends group. And then we offered all of them ice cream in exchange for twice a week emailing us and letting us know if they had flu symptoms in the last 3 days. Plus, we got their permission to get their UHS records, but only for the flu. Did they have the flu or not? Did they show up? And so we tested this idea to see, could we invent a better mousetrap? So remember, the predictions are that the curves will be shifted to the left, just like I showed you, and here's the actual data from the epidemic of influenza at Harvard. We were able to see that on average, the epidemic in the Friends group peaked 2 weeks before the epidemic in the random group, and actually the curve was shifted to the left, and the first statistically noticeable dispersion in the curves occurred 6 weeks before the epidemic struck. So think about what this means. The current state of affairs for understanding the epidemics in our country consists of individuals, like at the CDC, sitting in Atlanta and waiting for data. They collect information from doctors' reports around the country. Patients come and see the doctors say you have influenza, or they send blood tests for syphilis or other kinds of things. This information then is then collected in Atlanta, and then weeks from now, they know where the epidemic is today. About 2 years ago, an idea was published about Google flu trends, which said, well, if we're Google and we can observe people's searching behavior on a daily basis, today we can know where the flu epidemic is today. This was seen as a huge idea and a big advance. But what I've just told you is that actually with this method, you can predict not where the flu was 6 weeks ago, not where it is today, but where it will be 6 weeks from now, by taking advantage of the strategic location of individuals within the system and monitoring and plotting it. So here's the network of Harvard students, now it was unnecessary to map this network. All we needed to do is do the friendship thing that I showed you, but because we had the data, because people nominated their friends and it was a closed system, you could do this friendship paradox idea with a whole nation if you wanted, pick 1,000 random Americans and have them nominate their friends. Those people wouldn't be interconnected, but because we did it with Harvard students, I nominate you as my friend, by dumb luck you nominate her, she nominates her, you nominate me back. Actually, we could map the network. And here's a network of 1,700 Harvard undergraduates. Actually, this says 714 on them. And in a minute, I'm going to animate this network, and we're going to take daily cuts through the network for the whole epidemic, 120 days, all right? Now, this network, unlike other images I've shown you earlier in the class, isn't going to change across time, because your friendships, while fluid, don't actually change on a day-to-day basis, at least ignorably so. So the network is going to be fixed. This is the network. And the dots are going to become red if they're an influenza case and yellow if you're friends of an influenza case. Then we're going to make the node size proportional to the number of friends that you have that are infected. So here we are. We're going to start September 1st, 2009. I don't know where these two gentlemen were. Maybe you can find yourselves in the network. Here the epidemic is beginning. We're getting to the end of now October. Bang, 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 the epidemic growth curve. You get a kind of blooming around the red dots, and a preferential attack in the center of the system compared to the periphery of the system. And then you begin to get the flattening portion of the curve. You get fewer and fewer cases that appear. Believe it or not, we are among the first to have this kind of data to map networks with this level of specificity and the outbreak on a daily basis. And in fact, the intuitions that I cultivated in you earlier showed that the days of early detection depended on the 3 properties that we discussed. So higher degree, people with more friends got the flu about 10 days earlier than people with fewer friends. More central people got it about 5 days earlier, and people with low transitivity got it about 15 days earlier. All 3 of the properties that we discussed. And how much warning you could get if you built this mousetrap and trying to predict the course of epidemics, how much advance warning you could get by monitoring the friends of randomly chosen people will depend on a number of things. It's going to depend, first of all, on the intrinsic properties of the item that's spreading, okay? So the germ itself has something to say about whether or not you'll get 2 weeks advance warning or 2 months or 2 years advance warning. It'll depend on how you ascertain the infection, like what are the kinds of techniques you use to measure whether cases are infected. It's going to depend on the nature of the population. It's going to depend on the topology of the network for reasons we already discussed. And it's also going to depend on this very difficult issue known as network deformation. What if, as you were infected by this germ, it killed you, and you just lived long enough to transmit it to the next person? So, or what if it's information that's spreading, and as you say bad gossip to your friends, they say, oh, this guy's a jerk, I don't want to be friends with him anymore, and they cut the ties to you, all right? So if the flow of the thing through the system changes the topology, it creates all kinds of other complications which you need to take into account ideally. And the nature of the population example might be, for instance, the prevalence of resistance to the germ. Let's say you have a population with the same network structure, but in this population, 50% of you are resistant to the germ, and in this population, 100% of you are resistant. If you're, in this population where 100% are resistant, it doesn't matter whether you're central or peripheral, no one's going to get the epidemic, okay? So you need some additional information. And as I've been suggesting, this method is not restricted to germs, but can be used for anything that spreads in populations by person-to-person means, including a variety of health behaviors that we've discussed. So it's not just pathogens, information, norms, or behaviors. I think this is a famous pillow fight on a college campus. I forgot which campus they do this every year, can spread within the system. But a key thing is that for this method to be useful, the thing in question must spread interpersonally, at least in part. And it cannot affect people independently, for example, via a broadcast mechanism. So this method will not work with malaria. Why? Yeah. Yeah, the mosquito vector. So the mosquitoes fly in from the heavens. Like if I have malaria contacting with you, I can't give you malaria, okay? More subtly, so it has to be something that spreads interpersonally for this thing to work, right? If it doesn't spread interpersonally, this trick won't work. Or here's another example. Okay, here I am, and I'm about to be affected by this gentleman's behavior, okay? He's about to buy something, and now the question is, will the method work in predicting whether I will buy it? What if he buys an iPad? Do you think that Dan's iPad purchasing behavior is going to affect my iPad purchasing behavior? Yes or no? Are you guys affected in your purchasing behavior by what your friends are buying? Yes. So if you have random individuals and they nominate their friends, and you monitor the purchasing behavior of the friends, you can forecast demand for products in our society. But now what if instead of buying an iPad, Dan buys some tires? Do you think that Dan's tire purchasing behavior is going to affect my tire purchasing behavior? No, that's exactly right. So it's not just germs versus products, for example. Within the category of products, we have to have some suspicion that there's interpersonal influence in this purchasing behavior. And then and only then will this trick be useful in predicting and forecasting demand for the products. Conversely, if there's an advertising campaign for tires or for iPads, that will affect everybody, whether it's an iPad or a tire product. It rains from the heavens, the signal. It doesn't rely on interpersonal spread. Now, what's interesting to me is that we can use data from phone companies, from email providers, from online networks, and other sources to generate network maps and also to track pertinent behaviors and attitudes in this kind of brave new big data world that we are in. And such data could be used to identify friends of randomly chosen people. For instance, this is data from a real European country, part of a network of 8 million phone users where we were able to map the phone communications anonymized of all 8 million people. And so you can create a network map of the whole nation, and you can begin to think, my goodness, if I could contact those people and ask them if they would be willing to be censors for me, I could create a nationwide monitoring system for epidemic outbreaks. Now, in the coming weeks, some of you may see advertisements for this on the T here in Boston, because we're trying to do that. And if you see that, we're offering, I forgot, 40 or 80 bucks for subjects. Please sign up for it and participate if you want to. So we're actually trying to, you sign up to send text messages, do a little text-based survey a couple of times a week for a few weeks. So you could do that. What if you're the phone company and it's not a germ that's spreading that you want to monitor, but product adoption, for example? If you're the phone company, you not only know people's network interactions, but you also know what they're buying. And so then you can use these data in this type of a clever way. And in fact, we can use people as sensors in all sorts of ways. We are, in an era of massive passive data collection. And we can harness huge amounts of naturally collected data. And these new technologies allow us to track people, where they are, who they are talking to, what they're buying, and what they're writing, all subject to proper ethical review and anonymization and constraints. But this will open up whole new ways of understanding social systems and social processes. For example, if we could passively monitor truckers' purchases of fuel, we can use that as an early indicator of a recovering economy. Or we can monitor traffic jams in real time using cell phone motion. This blows my mind. Let's say you have a nation of people, like we do, of people with cell phones. If I wanted to map if I'm the phone company and I want to create a road map of the United States, I can do that by looking at how all of you guys, you little particles, are displacing across space, right? I have a grid. there are no streets on this grid, and instead I look at the flow of human beings carrying their cell phones through the system, eventually I can map the whole grid. Is everyone with me so far? Okay, but then what I can do is, because not only do I know your position in space, I know your velocity, I can see the speed at which you're traveling. And I see you guys are traveling on Route 95, I know you're on Route 95, and I know the speed that you're going. But if I'm the phone company, I can also see that you're slowing down. In fact, you come to a complete stop on Route 95. First, I use the data to map the streets. Then, having done that, I follow the motion of the particles, and now I see that a group of you is slowing down on Route 95 this moment. What does that mean? There's a traffic jam. Then what do? In real time, I process the data. I say traffic jam has just occurred here, and I feed the data back to my subscribers, but not to all of my subscribers. I don't need to broadcast to everyone in the country that there's a traffic jam at this location on Route 95. No, I only have to broadcast it to those specific ones of my subscribers that are also in Route 95 behind the traffic jam. Isn't that unbelievable? We can create a real-time monitoring of traffic jams in the whole country and instantaneously give information back to only the affected individuals in this all exploiting the kind of passive data that's being collected right now. Or we can track doctors prescribing medications within networks with respect to product adoption, as I showed you last time. Or we can track purchasing behaviors in personal networks to discern social influences or consumer choice. And in fact, there are 3 ways that this massive passive data can be used: either passively, where we have no contact with the subjects; quasi-active, like the Harvard example I gave you, where we needed some participation because we were accessing sensitive health records and we wanted people to consent; or active, where you, for example, impanel a group of people whose behaviors you wish to monitor by their participation. For example, people could sign up to be sensors and text their temperature every day as part of some kind of phone network, for example, and so forth. So the availability of these data about human behavior heralds what in my mind is an onset of a new kind of computational social science. And the availability of data of this kind is still increasing and will continue to increase, of course. So we have, of course, telephony data, internet data, query logs, links, and websites, video cameras in cities. Soon there are going to be cameras, people, even on our Google glasses in your lifetime in 10 years. RFID devices are getting sufficiently small and cheap that soon you'll have little embedded RFIDs in most of the products that we buy. Administrative records, transaction records, geographic information, voluntary losses of anonymity. People sign up for data wikis and stuff. Or eventually personal genomics, which I think will contribute a whole other set of big data that people could potentially use. And the question becomes, given this sort of new era of computational social science, what are the big intellectual questions that such data might be put in the service of? So there's a big debate that's happening right now among social scientists, which is, initially there was all this enthusiasm about so-called big data, and then now you have the Empire Strikes Back. Hardcore social scientists are saying, well, that's just data mining. Data mining without any guiding theory is nonsensical, and there's a big debate about whether or not, what's the relative importance of theory and hypotheses and data in understanding the world. Of course, the answer is that both are required, but we need to specify what are the big intellectual questions, what are the cool questions, how can we exploit big data to make the world a better place. So I think that so more careful and more complete observations of the world are great. But the question is, in the service of what? Will this data collection, in its breadth and detail, prove to be like the data that Tycho Brahe collected and that Kepler analyzed? Or instead, will it be a distracting profusion of noise? And of course, Tycho was onto something. In 1563, at the age of 17, here's what Tycho wrote, and I'll leave you with this. Here's what he said. I've studied all available charts of the planets and stars, and none of them match the others. There are just as many measurements and methods as there are astronomers, and they all disagree. What's needed is a long-term project with the aim of mapping the heavens, conducted from a single location over a period of several years. And in fact, that's what I think we are in the era of right now in the social sciences. We are acquiring Tycho Brahe kind of level of detailed information that is going to foster the emergence or support the emergence of a number of Keplers who can understand social processes. And I think that with this science, we can understand how exactly the whole comes to be greater than the sum of its parts. And we can use these insights, understanding each of our little behaviors and how we contribute to a greater collectivity, we can use these insights in ways that will make the world better, in ways that I've shown you today and will continue next time. See you then.